Welcome to the fascinating world of physics, specifically the study of electric charges and fields, as outlined in the CBSE Class 12 curriculum. In this chapter, we begin by understanding the fundamental concept of electric charge. Electric charge arises from the excess or deficiency of electrons in an atom. When an atom gains extra electrons, it becomes negatively charged, and when it loses electrons, it becomes positively charged. Basic unit of charge is the coulomb, and the smallest possible charge is the electronic charge, valued at 1.6 x 10 coulombs. This concept is crucial because it forms the foundation for all further discussions about electric forces and fields. The behavior of charges, how like charges repel and unlike charges attract, sets the stage for exploring the laws that govern their interactions. Let's delve deeper into how these charges interact and the laws that describe their behavior. Now that we understand what electric charge is, let's explore how these charges interact. Coulomb's law describes the force between two-point charges. It is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. This law applies whether the charges attract or repel each other. The force acts along the line joining the two charges. Medium between the charges also affects the force, with different materials having different dielectric constants. For example, air and vacuum have a constant close to 1 while water's is much higher. The law can also be expressed in vector form, accounting for both magnitude and direction. When more than two charges are present, the principle of superposition comes into play. This principle states that the total force on any charge is the vector sum of the forces exerted by all other charges individually. This concept is vital for solving complex problems involving multiple charges. Moving forward, let's discuss electric fields and the concept of electric dipoles. An electric field is the region around a charged object where another charge experiences a force. The strength of this field at any point is called electric field intensity, which is a vector quantity. It's defined as the force per unit positive test charge placed at that point. The direction of the field depends on whether the source charge is positive or negative. Now consider an electric dipole, which consists of two equal and opposite charges separated by a small distance. The dipole moment, a vector quantity, points from the negative to the positive charge and is calculated as the product of one charge and the distance between them. Dipoles are important in understanding molecular behavior and the effects of electric fields on matter. The torque experienced by a dipole in a uniform electric field causes it to align with the field, a concept that has practical applications in physics and chemistry. Further understand electric fields, we introduce Gauss's theorem. This theorem states that the total electric flux through a closed surface is proportional to the total charge enclosed within that surface. It's a powerful tool for calculating electric fields in situations with high symmetry, such as spheres, cylinders, or planes. Gauss's theorem simplifies the process of finding electric field intensity due to various charge distributions, including line charges, charged shells, and infinite sheet. By applying this theorem, we can deduce Coulomb's law and solve complex problems more efficiently. The concept of electric flux, which measures the number of electric field lines passing through a given area, is central to Gauss's theorem. Understanding these principles not only helps in academic studies, but also lays the groundwork for advanced topics in electromagnetism and technology.